You're tramping through unfamiliar woods, the light is beginning to fade, and you realize you're genuinely and utterly lost. The old ways, a compass and a paper map, require patience and a steady hand. But your phone instantly produces a tidy little blue dot, sitting squarely on a digital path, announcing your position to within a few meters. It feels rather like sorcery. But it isn't. It's simply a brilliant trick of timing, playing out entirely in the cold vacuum of space. I dare say you've probably muttered the acronym 1,000 times without ever unpacking the rather marvelous machinery hidden inside it. GPS stands for Global Positioning System, and understanding how it actually works requires a brisk walk down a ladder of clever ideas. We'll begin with the most ghastly and ineffective method your phone could use to find you, and step steadily down to the brilliant, almost absurdly simple trick it relies on instead. Allow me to explain. Imagine, if you'll, the absolute worst way to work out where you're. Let's call this approach the magic database of everywhere. In this dreadful scenario, your phone would need an enormous master list stored in its memory. This list would contain the precise location of every single tree, building, hill, and road on the entire planet. To figure out its position, your phone would look out at the world, spot a rather distinctive oak tree, consult its giant internal list, and declare, that particular oak is at these exact coordinates, therefore I must be right next to it. How perfectly absurd. The data alone would be impossibly heavy. The storage required on your device would be astronomical, and it still wouldn't solve the core problem. Knowing where a landmark is doesn't tell you how far away from it you happen to be standing. It's a terribly romantic idea, wandering and recognizing old friends in the landscape, but as a mathematical method for positioning, it's a total failure. So, we step down the ladder to a slightly less ghastly idea. Instead of recognizing physical landmarks, your phone decides to measure the physical distance to a single satellite sitting high above the atmosphere. This is the range-finding approach. Your phone sends a polite shout up to the satellite. The satellite hears this shout and immediately shouts back. Your phone times how long the journey took. Because radio waves always travel at a fixed speed, which happens to be the speed of light, multiplying that time by the speed gives you a precise distance. Let's say your phone calculates that it's exactly 20,000 kilometers away from satellite A. That's a jolly good piece of maths, but it leaves you with a rather perplexing geometric problem. Imagine drawing the solid line from the satellite down to the Earth's surface, measuring exactly 20,000 kilometers. Your phone could be anywhere on the surface of an absolutely massive sphere. If you chop that sphere in half where it meets the Earth, it creates a vast circular ring. You might be at the northern edge of that ring, the southern tip, or anywhere along the perimeter. One distance to one satellite simply narrows your location down to a gigantic circle drawn across the globe. We're making progress, but you're still utterly, hopelessly lost. We must descend further down our ladder. To fix the problem of the giant circle, your phone brings in a second spacecraft, satellite B. It performs exactly the same timing trick, measuring the precise distance to this second satellite. Let's assume it calculates that it's 21,000 kilometers away from satellite B. Now you've two overlapping bubbles of distance. When you press two massive spheres together, they intersect along a flat, circular plane. It's rather like pressing two soft balls of dough together and looking at the flat seam where they meet. This intersection shrinks your possible location from a massive, surface-hugging ring into a much narrower, two-dimensional hoop suspended in the sky. You know you must be standing somewhere on that specific hoop, but a hoop still stretches over hundreds of kilometers of the Earth's surface. You could be standing in a field in Somerset or on a dock in Nova Scotia. It's an improvement, I grant you, but you still couldn't confidently walk to the village shop. We're getting terribly close, though. One simply must have a third point of reference. Enter satellite C. Your phone measures the distance to a third satellite and constructs a third invisible sphere of distance. When this third sphere presses against the hoop created by the first two, something rather magical happens. Three spheres can only ever intersect at two distinct points. One of these mathematical points is usually floating thousands of miles out in deep space, which is highly unlikely to be your current location unless you've had a rather severe accident. The other point is sitting squarely on the surface of the Earth. By dismissing the point that's drifting in the void, your phone is left with exactly one solid, logical answer. It drops the little blue dot right on the digital map. This elegant intersection of three distances is known as trilateration. It's the true beating heart of the entire system. You're no longer lost. However, you might have noticed a creeping issue. This entire, splendid geometric trick relies entirely on measuring time. If your timing is off by even a fraction of a microsecond, that blue dot won't just be a few steps away, it will be miles off because the speed of light is so dreadfully quick. The atomic clocks living on the satellites are frightfully expensive and remarkably accurate. They measure time by tracking the vibration of atoms, losing barely a second every 100,000 years. But your humble mobile phone has a rather cheap, basic clock inside it. Left to its own devices, your phone's internal clock would drift wildly, and the blue dot would smear across the map like spilt ink. So, your phone uses a fourth satellite to correct its own pitiful timing. By checking its calculation against a fourth point of reference, the phone realizes its own clock is running slightly fast or slow. It adjusts its internal time to match the precise master clocks on the satellites. Once the phone corrects its own time, the blue dot snaps sharply into place. You don't just get your location from this fourth measurement, you get perfect time as well. There's, however, one final invisible dragon to slay on our journey down the ladder. The radio signals from those satellites are traveling through the Earth's atmosphere. The layer of charged particles at the very edge of space and the wet, gloomy air closer to the ground actually slow the signals down. It's rather like trying to sprint through a muddy field. If the phone simply assumes the signal traveled at a perfectly constant speed, the distance calculation would be wrong. This is why your modern phone doesn't just rely on the American GPS satellites. It listens to the Russian system, the European system, and the Chinese system. More satellites in different orbits provide overlapping signals that help your phone model the weather and the atmosphere, correcting for the muddy signals. It calculates the atmospheric drag on the fly, adjusting the maths until the blue dot is precise enough to tell you which side of the street you're standing on. So, the little blue dot isn't magic, and it certainly isn't a secret map of every tree on the planet. It's just a brilliant cascade of geometry, cheap clocks borrowing perfect time from space, and radio waves navigating the weather. A wonderfully clear chain of logic, proving that you're never truly lost as long as you're willing to do a little maths. Before we part ways, I have a rather specific question for you to ponder and leave your thoughts on in the comments below. If you were forced to navigate entirely without any form of digital assistance for a whole month, would you prefer to use a paper map and a magnetic compass, or would you rely on navigating by the stars and the sun? Do tell me which ancient method you trust more and why. If untangling this invisible web of satellites and geometry has brought you a moment of clarity today, do pass the video along to a friend who still believes their phone is somehow taking photographs of them from orbit. A generous thumbs up tells the algorithm this elegant lesson deserves a wider audience. And naturally, you simply must subscribe to the channel so we may continue unraveling the hidden mechanics of the everyday world together.